Hey folks, Quillian here, and welcome to another episode of our C# tutorial for complete beginners. Last episode, and for part of this episode, we've actually been dealing with something that isn't about learning C# exactly. It's about messing around with a little bit of a programming technique, of course, programmed here in C#, but we're trying to normalize the speed of the game because we were running into this thing where the enemy moves one tile to the left every single tick of the update. And at first that was running infinitely fast. Well, now we are sleeping between each update, or each frame is a way to think about it. We're sleeping the amount of time required to lock our frame rate to 30 frames per second. But this has all kinds of different problems. Higher frame rate leads to smoother gameplay. That's great. But now it still means our enemy unit moves once every 30th of a frame. Every 33 milliseconds, our enemy moves. And there's no way for us to tune the speed of the enemy beyond changing the frame rate, which is not very good. Not only that, but this is also limits the speed of our player, because our player only updates once per frame as well. And actually, now that we're delaying the game a bit, there's actually a little thing where your keyboard repeat rate can exceed the like the frame rate basically. And so there's this little thing that goes on right now where I let go of the key and your character keeps moving for a little bit longer. It's actually even more obvious if I'm going like moving vertically here, because the way the movement is processed. See, it actually overran, and we're still not checking to make sure that we're staying within bounds when we're doing our user movement, which means I could exceed it and we throw our exception. This is our intentional exception that we're throwing there when a unit attempts to move out of bounds. But our player, we should actually verify that the player can't. But there's that filling of the keyboard buffer is also undesirable. And there's two ways that we're going to resolve that. But let's keep focusing on the enemy for now. And the fact that right now the enemy moves once per frame, so our frame rate determines the speed of the enemy. That's no good. That is double plus ungood. So what we're going to do is we're going to make a change here to update. I mean, we're still going to replace this ultimately. Don't worry, we're going to replace this in a moment. But what we're going to do is we're going to change update so that update knows how much time has passed since the last time update was called. And what this means is now a unit is going to be aware of the passage of time, which means, for example, our enemy unit could just could have a movement rate that is completely independent of the frame rate. And we're going to take a look at that. So what I'm going to do is in our unit class, this is our base class. It's actually an abstract class. We never instantiate this directly, but that's okay. I'm going to make a change to the update function over here. I'm going to say this is going to require, and for us, this is going to be an integer of delta time in milliseconds. Okay? Now, if you've done any work in Unity, or if you watched any of my Unity tutorials, you can see that delta time is a parameter that does get passed to the update function in Unity, except there it is a floating point number. It's a decimal number, and the delta time in Unity is in seconds. Although, because it's a decimal number, usually it's getting passed something like 0.03, seconds. So, it's effectively getting past numbers that are just milliseconds long, but as a decimal point. So again, in Unity, it'd be a float, which means you'd probably expect something like 0.03, but we are going to use an integer of milliseconds. So we're going to expect a whole number like 33 milliseconds since the last update. Now, we still don't do anything here. At some point we might. I don't know, or maybe this could become a completely abstract function. Who knows? But for now, we're just going to do this and not really do anything, and that's okay. But in our player unit, in fact, we'd actually now get an error over here, because we're saying that we are overriding a public void update that doesn't take any parameters, and the compiler here is letting us know, hey, you're trying to override something that doesn't exist in your parent. Are you sure you're doing the right thing? Now, we could just say, well, we're not overriding anything. We're just, this is a completely different function, completely. But that's not what we're doing. We are, in fact, wanting to override the base update, but now we also have to take in a single integer to match the signature of our parent. So we're going to have to accept that, and we'll have to do the same thing for enemy unit over here. Now, for now, enemy unit is the only one we're going to care about. For the enemy unit, I'm going to set up a couple of variables over here. I'm going to set one to be a public property. It's going to be a public integer that is going to be something like time between moves. And I'm going to have a default to something like, I don't know, let's say it's going to take 100 milliseconds. It's going to be quite slow. 100 milliseconds between moves for the enemy. I want to put it quite high so we'll be able to tell that it's not actually running every single frame. Okay, because right now our frames happen every 33 milliseconds. So basically this means our enemy is only going to move every third frame, more or less. Every third frame our enemy is going to move. And then what we're going to do is we're going to have a private variable here called time since last move, which is going to start off at 0. I don't have to set this explicitly. It would have assumed that. But we're going to do this. Now, by convention, you tend to capitalize the first letter of your public properties or public fields. Really, this is just a public integer as is. We may want to convert this into a property with a setter and a getter. But here, I think it's totally fine that things from outside of our program can fiddle with, or from outside of our class can fiddle with this. I can't imagine any sort of restriction required. I mean, I guess if you put a negative number in here, it might act a little bit weird, but that would be the same as saying like move instantly. So you know what, we'll just set it like this for now. It's going to be okay. And then this private one, which is how we track the time since the last time we moved. So here's what we're going to do. At the start of our update over here, we're going to check before we do our AI. We're going to say, has enough time passed that we should be moving? Question mark. So what I'm going to do is I'm going to say our time since the last move, we're going to add, I'm going to say, is it going to be equal to the time since last move plus delta time in milliseconds. So this is going to be this sort of counter to the cruise values. And right now, because we have our fixed frame rate, this is going to be told the delta time is 33 milliseconds. So the first time through, time since last move is going to be 0. Then we're going to add 33 milliseconds. The next time it could become 66, 99, and then 132. Math is hard. I probably got it wrong, but I don't know. So we're going to accrue that. By the way, there is a shorter way of writing this. I think I've pointed out before, but you could say plus equals. That's exactly the same. What this will do is it's exactly the same as saying time since last move is equal to time since last move plus delta time. So this just adds this amount into there and then resaves the variable, which is quite handy. So we're going to add that. Then we're going to say if time since last move is less than time between moves, then that means not enough time has passed. Let's not do anything. So what we're going to do here is we're just going to return. Now, we haven't looked at functions that much, but functions can return values. We talked about how these are voids. They don't return anything at all, but some things can return values. And this is not returning anything, but you can still call return. And what this will do is this exits the function. It quits the function right away. So if the time since last move is less than the time between moves, we just bail. Just stop. GG. We're done. Otherwise, if we get here, it means we need to make a move. So what we could do at this point is set time since last move to be equal to 0. Right? Because we're making a move right now. So we're making a move, so we're going to set time since last move is equal to 0. However, what that would happen here is that, remember when I went through the counts here? First time through, this starts at 0, then we add 33, so it becomes 33. Then 33 is less than 100, so we exit. The next time this becomes 66. 66 is less than 100, so we exit. Then it becomes 99. 99 is less than 100, so we exit. Then the next time it becomes 132. 132 is not less than 100, so we do not exit. So we could set time since last move to 0 over here, but that means we sort of like lost that extra 32, because we're supposed to move every 100 milliseconds, right? What if instead we just subtract the time between moves? That would leave time since last move to be equal to 33, right? It went from 133 to 33. That way, over the course of a longer program, it will average out to correctly moving every 100 milliseconds. It doesn't always move exactly every 100 milliseconds. Sometimes it'll be 132 milliseconds between. Another time it might end up only being like 87 milliseconds in between, just because of how the chunks line up. Now, this is only really a problem if your actual delta time is quite large. If our frame rate is running faster and faster and faster, right? If we're getting more frames per second, then the time between frames becomes shorter and shorter and shorter, and so this will become more and more accurate. In a perfect situation, if we were running 100 frames per second, if we were running 1,000 frames per second, then update would always have a delta time of 1 millisecond, which means we'd always create our moves at exactly the right time. But in general, this is going to be fine. Hell, actually, here, as long as delta time is some like multiple of the 100 we have set here, so if we were running 100 frames per second, delta time would be 10 milliseconds, which means we would correctly run every 10 frames, we would advance our counter by 1. But this means over the average course of a program, regardless of what a frame rate is, and especially if our frame rate is unsteady, because sometimes the program might run really fast, and other times it might run a little bit slower, depending on how much stuff is going on, and how much stuff, maybe in the background Steam started downloading an update or something like that, and is applying a big patch, so your computer all of a sudden slows down. You don't always run at exactly the same frame rate, which is what we're going to look at in a second. So there we go. So we're going to do this. Now, regardless of what frame rate, our enemy should take exactly the same time to move from the right side of the screen to the left. So let's give that a try. Let's drop our frame rate to 10 frames per second. Very slow. Oh, we get an error here because our update routines need to know the time, right? They need to know the delta time. So we're going to go ahead and pass this delta time to there. We can compile. Yeah, okay. Oh yeah, we call the base one. The base one requires that we pass, the delta time ms. So this is inside the enemy units update. We call the base one, and probably the player update is going to do the same. Yeah. So we have to keep passing the delta time ms up the chain. Compile, build successful. Excellent. So we're going to run at 10 frames per second. It's going to be very chunky and choppy, but it's going to take, we could even calculate it because we know he moves 1 square every 100 milliseconds, so 10 squares per second. The screen is 80 characters wide, so it should take 8 seconds to go from the right side to the left side. Does that sound about right? 0, 1, 2, 3, 4, it's halfway, 5, 6, 7, 8. I mean, I'm not good at counting, time perfectly, but that seemed to take about 8 seconds to go through. Let's try with 100 frames per second, which our computer should easily be able to do in this situation. And run this, 0, 1, 2, 3, 4, we're halfway, 5, 6, 7, 8. There you go. Whether we're running at 10 frames per second or 100 frames per second, it takes our enemy the same amount of time to go from one side of the screen to the other. Now, this sort of system here, the time between moves or time since last move, I use this a lot. I really like this little mechanic, but there's lots of different ways to sort of arrange this internally and keep track of this. It's sort of like a cooldown. The cooldown between moves is what's being represented here. Okay, so there's that, but we still don't like a fixed frame rate. How do we remove the fixed frame rate? Well, is there any way for us to know how much actual time it took? So let's say we don't care about frame rate, right? Boom. Okay, we don't care what frame rate that's not entirely accurate. We are happy to run at any frame rate whatsoever. However, we do need to know how much time each frame is taking. So how could we tell that? Because we need this delta time ms to be filled out. And right now, we were reliant on that desired FPS, but we don't have that anymore. I'm removing that. So how do we know? Well, one part of the standard C# library, well, there's a few different ways, but one of the tools that's in the standard C# library is something called stopwatch, which is really, really handy. But basically, what we need to know is we need to be aware of time passing by. There are multiple time libraries in C#. There's ways to ask the thread how long it's been running. There's lots of different things. But what's one of the handiest is the stopwatch class. Now, the stopwatch class is technically part of system.diagnostics because it can be used to benchmark things, figure out if things are running fast, slow, that sort of thing. Here, we're just going to use it to find out how much time is passing from the start of the game. So when our game launches, we're going to keep a stopwatch around. I'm going to make a private stopwatch called stopwatch. This is a private, so it should be lowercase, like that. So we're going to keep a stopwatch around. What are you complaining about? Wait. Does MonoDevelop not have the stopwatch? That's possible. Oh, crap. Okay, well, that was quite interesting. Sorry, something came up that I didn't expect. Huh, curious. Well, even though we've been using plenty of things in systems so far, to use system diagnostics, for some reason, we have to explicitly make sure that we include a reference in our project setup over here, which is just a little bit odd to me. Why that was required for this specifically. There's probably something I wasn't aware of, but what we have to do to be able to use the stopwatch, which we can, it's perfectly fine, which is good because that's the one I really like using. If you go over here into your solution, then your project, so Dodge game, we've got references over here. If you right click on references and hit edit references, this is a lot of things that you can include as a reference in your project. Just make sure you go down to system over here, just system by itself, and turn on the checkbox. And then that's fine. So it's kind of weird to me that despite including the using over here, it wasn't sort of automatically pulling in that reference. And clearly there's something I'm not quite getting with the compilation or reference system here in, I don't know if it's C# in general or just Xamarin Studio's implementation. But as long as you include the reference to system here, now we can use system diagnostic stopwatch. So there we go. All right. So we've got that. And what are we going to do with this thing? So I've declared we've got a variable here called stopwatch. But right now it doesn't contain anything. It's just null. We have to instantiate the stopwatch. And we're going to do that as part of our game's constructor over here. All right. This is our constructor. It gets run automatically when a new instance of game is created. So as part of that, we set up the player unit, the enemy unit. We're also going to go in and instantiate the stopwatch. So stopwatch is equal to a new stopwatch. Now notice the order of this, in a sense, it looks like it doesn't matter. You're like, well, here I'm referencing the stopwatch variable, but I'm only defining it down here. Why is that okay? Well, the reason that it's okay is because the way our class gets processed, it gets entirely loaded in memory first. Like, it reads the entire class definition. Our class as a whole knows that this member variable is supposed to exist within game. And then it's afterwards that this function gets run and it's referencing a member variable. We couldn't do the same thing here. If we define some sort of integer called a, and then we tried to assign a, whoops, nice autocomplete. Stop autocompleting. Thank you. It's because this is so not valid. You can't do this. If I tried to compile it, it says cannot use a local variable a before it's declared, but it's a little bit different with class stuff. All right, let me clear that out. So now we've instantiated a new stopwatch. What can you do with a stopwatch? Well, you can start it, you can stop it, and one of the things I like quite a bit is you can pause a stopwatch. You can also reset it. Well, really, stop just stops measuring it. It doesn't reset. So you can start a stopwatch, stop it, start it again, stop it, start it again, stop it, reset the stopwatch, and then start it over from scratch. And the reason, that's why I like the stopwatch system, is because you can do that. If you pause the game, you probably want the stopwatch to stop. Right? Even though, if you open up a main menu, for example, your program's still running because you're interacting with the main menu in some sort of fashion, but the game itself is not supposed to be running, so you would probably want to stop the stopwatch at that point. So yeah, so that's why I like to use this as opposed to a few other methods for keeping track of time. And all this for the point of when we run, what we're going to do is when we run, we're going to start the stopwatch. Start. And what we're also going to do, and we can do this inside of run, because run is a single loop, right? Is I have an integer that says something like time at last frame, or previous frame, which is going to start off at 0. This is the number of milliseconds that has that the stopwatch reported last time around. Now, it should start at 0. I guess we could make sure. So our stopwatch it has a bunch of different functions and properties and things like that. But the one we care about is the elapsed milliseconds right over here. So what this does, this is a property that returns the number of milliseconds that has passed since the stopwatch was started. Now you see we're getting an error here. What's going on? Well, it's saying it can't convert a long to an int. Elapsed millisecond is actually a long integer. So just like we have float and double, both float and double are floating point numbers. They're decimal numbers. Float is single precision. Double is double precision, which normally you won't care about. Double precision you'll only need if you're tracking numbers that are extraordinarily small or extraordinarily large. For your average number, a float is going to be perfectly fine. It's not going to become imprecise any more than a double would. Same thing with an integer and a long integer. An integer holds whole numbers from negative some massively negative number to positive some massively positive number. Huge range. It partially depends on your computer, your architecture, 32-bit, 64-bit, all kinds of different internal stuff. You don't need to memorize what the numbers are, but they're quite large or very, negative one way or the other. A long, though, is even bigger than that, bigger minimum and maximum. And so our stopwatch keeps track of the milliseconds as a long because just in case this is a program that runs a really long time, the number of milliseconds since it started could be really long. So that's fair. Okay, so there's two ways we can solve this. One, we can say, okay, time at previous frame, it's not going to be a regular integer. It'll be a long integer. That's okay. Okay, that's fine. We can absolutely 100% do that. Alternatively, what we could have done is done a cast, which is something we haven't talked about before. We can say, all right, yes, I realize that elapsed milliseconds returns a long, but it's okay for you to force this long to become an integer. Now, if this number is actually bigger than an integer can handle, then, unexpected things may happen, then that's okay. But normally, this will be perfectly fine. But might as well go ahead and declare this to be a long. There's nothing wrong with that. Seems pretty good to me. Excellent. Why is this perma building? Every now and again, Xamarin Studio goes a little bit bonkers, I find. And it gets stuck doing this build until I close and reopen it. Oh well, that's okay. We'll deal with that afterwards. Yeah, so time at previous frame. So we're going to start it there. Now, almost certainly, this should return 0 the first time around. But let's just do this. So that's going to be okay. So instead, this delta time ms, this represents the time between frames, right? So we were setting up to a fixed number before, which, from this desired FPS, I just forced this 33 here so that I could actually compile things. We're going to change this. So delta time ms, the time since the last frame. What will that be? Well, the time since the last frame is going to be this, is going to be whatever stopwatch.elapsed milliseconds is now minus the time at previous frame. That will tell us the difference between the two, right? So let's say the first time around this is 0, and let's say we processed a frame. Let's say it took us 30 milliseconds to process the entire frame because, it took a long time to update the enemy AI or something like that. So it took 30 milliseconds. So on the second loop around, this elapsed millisecond is going to say 30, whereas time at previous frame will still say 0. So 30 minus 0 would be 0. So the delta time, the difference between the two frames, will be equal to 30, which is great. And then what we should do is then update the time at previous frame to this new time. So that delta time ms will always be correct. Now again, we get the underlined in red over here because these are longs and we're trying to stuff it into an int. Now, again, I could just turn this into a long, and then we'd still get a problem here. Like, I could do this quite easily, right? Turn delta time ms to a long, but then we get errors here because these are expecting integers, and we could keep going up the chain. But at some point, it's probably best, because longs take up more memory. Not that much more, but they do technically take up more memory. So if we don't need a long, and delta time ms will actually always be a really small number, so it's kind of a waste. Let's use this as an integer. That's okay. So that'll move the error back up here. And instead what we're going to do is we're going to say, listen, I'm going to wrap these in parentheses. Whoops. Oh, it doesn't. Really? In Xamarin, it doesn't automatically complete the parentheses. That's interesting. I'm pretty sure the mono-developed version I use, if I select this and do a parentheses, it just wraps it all. But I might be wrong. I might be thinking of Sublime Text or something. So this doesn't change the equation, right? This is just, it's just like when you write down a math equation, you can put parentheses around things. These are, in a sense, unnecessary. But it means that this will execute first, right? Or will resolve first. We'll do the subtraction. And the number that's left is still a long. Well, let's force that long into an integer at this point. Since this is always going to be a really small number, this integer is not going to overflow or do anything weird like that. We're not going to say, all right, subtract these two. The answer we've got, just stuff it into, treat it as an integer, and then stuff that number into here, and then we'll be happy, hunky-dory. Yeah, ignore that use var keyword. I deny the use of the var keyword completely. So now our delta time will actually be the correct time in between frames. Now, what we want to get rid of is we don't want to sleep this. All of a sudden, this doesn't make any sense, right? Because this is correctly the amount of time between frames, and then we don't want to sleep that amount of time, because that's not right, right? Do you know what I'm saying? In fact, how do I explain this more clearly? Because I feel like that was not a very good example. This, before, we were declaring how much time we should wait between frames, right? We were saying we are going to wait 33 milliseconds between frames. That's why we put in the sleep, because we're saying, no, wait 33 milliseconds now. But now, delta time ms is, we are not declaring how long to wait. Instead, delta time ms contains the actual information of how long it's been since the last frame. So then we don't have to sleep that time anymore. Now, it's possible, this might be a little odd, it's possible if our program runs so fast that it might take less than 1 millisecond to process a frame. Every now and again, we might do this and actually end up with a delta time ms of 0, which is technically okay because our enemy unit obviously won't move if the delta time ms is 0. But if that's the case, we're probably running insanely fast, right? And that's one thing with this console application. It could potentially run insanely fast. It'll run, unless, it's dealing with input or output stuff, it'll run at 100% of your CPU quite happily. It'll just keep looping in this little tight inner loop, processing things as quickly as possible. Maybe not doing anything, right? If time's not passing by, it might not be moving the enemy. If you're not hitting anything on the keyboard, it's not going to be moving the player unit. But this loop will loop at 100% of one of your CPUs on your computer. And that's, not necessarily a great thing, because we don't necessarily need that much processing power. I'm actually going to leave this little thread sleep in here, and I'm just going to say something like, let's just do a tiny sleep to avoid running at like a billion FPS, okay? Just to avoid running at like 1 billion frames per second. Or maybe we could say something like, if the delta time is super low. That's actually probably a good idea. If the delta time is like less than, 5 milliseconds, okay? No, I'm changing my mind. Sorry. We're just going to sleep for like 5 milliseconds, which means that the fastest frame rate we could possibly ever hit is like 200 frames per second. There's a bunch of different ways, and your big games don't really need to do this because they're usually, there we go, build finally canceled. They're actually waiting for inputs and outputs and the GPU and the frame rate. A lot of your big real games never hit 100% of your CPU because they're actually waiting for other things. They're reading things from the hard drive. They're pulling in information from RAM, doing a lot of data manipulation. They're sending things back and forth to the video card. So usually don't hit 100% of your CPU. You don't normally need to do this. But I'm doing it here because I think we could actually be in one of those crazy situations. So the nice thing about doing a tiny little sleep here is it guarantees that the time between frames will always be at least 5 milliseconds. In practice, it'll probably be 6 or 7, especially if we add a few more characters in here. So delta time ms will always at least end up being 5. But we don't know what it is. But if we run this, our character, remember, he's moving at a fixed rate of 1 square per 100 milliseconds. We don't know what frame rate we're running at. What, 1, 2, 3, 4, 5, 6, 7, 8. We have no idea what frame rate we're running at. We could be running as low as 10 frames per second because we have a crummy computer, or we could be running as high as, 200 frames per second because we're limited by the thread.sleep. But whatever it is, and it could be changing depending on background stuff on your computer. It could be running faster at one point, slower at another. If you have a complicated game, maybe there's a big complicated pathfinding request that just had to be put in, which just really ate up a lot of CPU activity and dropped your frame rate down a little bit for a moment. Regardless of what your frame rate ends up being, your character here, this character here, will always take 8 seconds to go from one side to another because the enemy unit is said your time between moves is 100 milliseconds. We could speed this enemy up. We say, listen, you know what? That was too sluggish. We want you to move every 20 milliseconds. We're going to run this and vroom. That's good. That's excellent. You're going to do that. And you can tune the behavior of the enemy completely independently of the frame rate. And you don't care about the frame rate at all, which is awesome. Okay, this wraps up the last of our non-C# stuff. We have one more true C# thing to do, which is arrays. And I was hoping to do it in this episode, but I think I ended up talking a little bit too long. So it probably makes sense to keep this sort of self-contained, put a cut in here. We're happy about this. Arrays are the things we're going to deal with next time, and arrays are, I think that arrays will be the final episode, unless it ends up being a 2-parter or something like that. It's a really useful structure for containing a lot of data, and really what we're going to use it for is having many, many enemies around. Oh, you know what we can do to sneak in here? This is not, so we'll do one more thing in this video, which again is not going to be like learning C# syntax, but is going to be a cool game thing. Right now we can't lose, right? The idea is, let me line up the player on the same row. So right now, our enemy spawns on row 17. Let's put our player on row 17 as well over here. So at some point, the enemy should smack into us. But right now, they just pass through one another, which is fine. At some point, the player unit and the enemy unit have exactly the same X and Y position, and that's okay. One gets drawn first, and then the other one gets drawn on top, like visually speaking. But other than that, they have no idea that they're existing in the same space. Oh yeah, no, for what I want to do, I really do need to... Well, no, that's okay. That's okay. Here's what I'm going to do. When the player does an update, let's have it check to see... how do I want to do this? Because really, in a sense, this is part of our array system. Okay, let's update both of our units. This is in our game, okay? Now that both units have moved, though they haven't been redrawn yet, but that's okay. They have both moved internally. Their X and Y coordinates have been updated. Let's see if the player is colliding with an enemy. If so, then game over. For now, that's just going to be game over. Okay, so how are we going to do that? Well, wouldn't it be handy if we'd be able to say something, and this is often the case. There's two ways of programming. There's sort of like from the lowest level or from the highest level. Often you actually end up sort of doing a little bit of both and meeting in between. An example of lowest level programming, like starting from the bottom, would be, hey, our unit needs an X and Y coordinate, so we're going to go and implement the X and Y coordinate and do a little bit of sanity checking to make sure we can't get an invalid X and Y coordinate. Okay? We're starting from the bottom. An example of starting higher up is here, over here, we're going to be like, wouldn't it be great if we could say something like, if player unit dot is colliding with enemy unit. I mean, we don't have a function called is colliding with, but like conceptually we're like, yeah, that would be good. Then game over. Oh yeah, I like that. Okay, so we need this sort of is colliding with function. Now, this is something we're calling on player unit. We could add it to the player unit class, but to me it sounds like the sort of thing that probably belongs to just the base unit class. We might want to know at any time if any one unit is colliding with any other unit. Yeah, okay, I like that. There's no reason that this requires any player-specific knowledge. So in unit, we're going to make a public function that returns a Boolean. It's returning true or false. Is colliding with, and then other unit. So this is a class method that, why you red? Oh, because we're not returning anything yet. Yeah, it's saying like, well, you say this is a Boolean, it's got to return true or false, but we're not returning anything yet. All right, let me get back to you. Anyway, to get rid of the error, we're just going to say, let's assume no collision right now. There we go, good. So there's going to be two units in this function. Because this is a method that belongs to an object, an instance method, we have this is the current unit, unit, and other unit, actually I'll just call it other. I like it. Other. We could also call it that. This and that. but I usually like to say other. I like that. Other is the other unit. So are the two of them colliding? How can we check in what situation would is colliding with be true? Well, they're colliding with each other if they occupy the same space, is what I'm going to say. So if this dot x is equal to the other dot x, and this dot y is equal to the other dot y, we are in the same square, so we are colliding. So then we can return true. So if our x's and y's are identical, then we are in the same square, so we are colliding, so we return true. Otherwise, we return false. So we could, you could put in an else here or something like that, but there's no reason to do that. It's just we check one situation, and if it's not that, we return false. And we could have a bunch of things that we check. If this, return true. If that, return true. If this other thing, return true. And then the base one is false. False, we're not colliding with each other. So this will now be happy. Excellent. And then game over. What do it mean to game over? Well, let's make a function. Let's make ourselves a function called, say, game over. So at some point, we do this. We call game over, and game over does something. What I think it should probably do is something like console.clear console, well, then the cursor is going to be at the top, which is fine. Tell you what, we'll do something like console.writeLine game over. And then I'm going to put the console.set cursor position. I'm going to move it to the bottom of the screen. So it's going to be on the left, and the bottommost row of the screen is console.windowHeight -1. Because again, this is sort of you think of it as an offset from the top. So window height is probably something like 24 rows. So this will put us where the y coordinate is 23, which is the bottommost row. So then we'll just set that at the bottom of the screen, and that should look okay. So can we compile that? Okay, we can. Good. Let me build this, and oh, there's the game over. It printed game over, but then our characters are still there. Why is it? Well, after this game over function runs, it'll, when it ends, we return to here, which means we just keep going. So after we do this, let's just break out of this run by returning. We're going to return out of the run function, which will stop our program. So let's try that. Boop, game over. Now press any key to continue, which closes the program. There we go. So now we have a loss condition. We could do a lot more with this. Maybe we don't want to return, or maybe we want to be able to set a flag here, try again, yes, no. But there's all sorts of different things we could do here. But for now, this simplicity is going to be okay. So now we have some sort of loss. So now it's a dodge game. We've got to dodge this X. Okay, that's pretty easy to do. We can confirm something else. If I move onto the X, I lose. Excellent, that's great. But only one thing to dodge is not very interesting. Also, with the enemies just sort of stopping on the left edge of the screen, that's also not very interesting. How are we going to resolve that? Well, that'll have to wait until next time. Thanks for watching. See you then. Thank you to all our August patrons, i.e. people who pledged in August and who are supporting videos from September through to early October. And especially these Mic Check supporters. We've got Ole Peter Talgo, Adam Conway, Drazion, Jan Torivel, Adjective, Michael McClintock, Aaron Toyson, Craig Mortel, Julian Auger-Lafont, Marius Fieldvold, Speedy Savant, Steven Stager, Valiant Cake Fiend, Wes Oldenboiving, Jason Yanity, Kale the Quick, Neil Blakey Milner, and Yukofin, and everyone who's watched, shared, favorited, and subscribed. Thanks for watching. See you next time.